Hi, and welcome to another in a series of Introduction to HPC videos. This one covers Linux, especially as it pertains to our HPC. So there are some really specific cases using Linux. You can use our graphical interface on demand for a lot of the things you do on our HPC, but understanding Linux is really helpful, and especially if you're getting into more frequent use and larger use cases. I just want to give a quick reference to Colorado University, University of Colorado in Boulder, as they provided some of the information for this course. So our HPC, just a super quick overview. You get free resources here. So you have large-scale computing, data storage, we offer consultations, and we have training materials. Puma is our latest cluster. It's about 2 years old now. It has 320 compute nodes, 30,000 cores. So if you compare that to a laptop with 4 cores, it's like a room full of laptops. It's really impressive. It would be stacked floor to ceiling. We have NVIDIA GPUs. Our older cluster, Ocelote, also has GPUs. They have P100s. The all-flash file system is directly mounted to the compute node, so that's super quick storage. And the allocations are free. So to get started, you need to connect. On a Mac, it's pretty easy. You can go to Applications, Utilities, and then Terminals from there. On Windows, we recommend using PuTTY. So we don't explain how to use PuTTY here, but in our documentation, there's instructions on step-by-step. And I've got a link here to On Demand. That's our GUI interface. And as I mentioned, it can do a lot of the functions that we can do by the command line. I have some reference information here. So to get started, you need an account. So there's a link to that. And to access your account, there's a link there in our documentation. Since you can't get to it straight from here, you can go to docs.hpc.arizona.edu and then navigate to account creation or system access. Also, there is a PDF of this workshop that's in our training under the documentation. So you can follow along on the PDF and follow any links. To get to the GUI interface, it's ood.hpc.arizona.edu in a browser, and you just follow the connection prompts from there. As I mentioned, this is about Linux, so this is probably the last reference will be to the GUI interface. Command line. So when you connect first and you're using SSH, your NetID at hpc.arizona.edu, you're going to connect to a Bastion host. This host has the name of Gatekeeper, and all it is a connection point to keep people out who aren't supposed to be connecting to our clusters. So you can't actually really get any work done on that Bastion host. It's really a point where you connect to the next step. And to get in next, you type shell. Shell takes you to one of the login nodes, and it's from there that you can actually get some of your real work done. So what is Linux? Linux has been around for many years. It started off as a workstation operating system, but even from the very beginning, it's been open source, which means it has a lot of flexibility, but some constraints. So there's trade-offs there. Windows is its own ecosystem where everything is strictly controlled, but you lose flexibility. So that's what you have to deal with. It is layers. So the first layer we deal with is hardware, which is going to be the same on let's take a workstation. The hardware exists, but then the OS kernel, the kernel is what talks to the operating system. So you don't need to issue commands that tell you where to put the data on the drive. The kernel and the drivers that are part of the operating system take care of that, and then layered on top is software. There are different versions of it available. So it starts as open source, but then there are companies that take that and put their layers on top, which make it proprietary, but then a more structured environment maybe has more security and more features built into it. So you can pay for some of those, like Red Hat, which is commonly referred to as RHEL, or SUSE is another one. Ubuntu is more open source. One of the really big advantages is that Linux is run on all kinds of servers and workstations and devices, from Raspberry Pis to the largest supercomputers. And really, all of the supercomputers are going to be running Linux of one kind or another. So why use Linux? So it's a default on the HPC systems and ours in particular. We don't do Windows on any of the compute nodes. It's very flexible, powerful, it's open source. The one that we've been using is CentOS. We'll probably be migrating to Rocky. It's another open source. We used to have Red Hat, but then the licensing got too expensive. But for the users, it's all kind of the same look and feel all the way through. So let's start with Linux itself and what it looks like. So we're going to start with the simplest of commands, ls, which is to list, and -l gives you a long list. And what are you going to list? My work directory. So you've got commands, flags, and targets. You should be logged in at this point, and you should be at the login node when the shell. So you should be able to type any of these commands in here. If you type ls-l my work directory, it doesn't exist, and you'll see a message about that because you haven't created it. In general, a lot of the commands have help with them, and it's man, short for manual. So man ls. The file system structure for Linux. So it's a way of organizing all of the files, and there is a consistency across all of the different Linux distributions, not entirely, but generally. And so you have files and directories, and you have file paths. So in this example here, /home, /user, /script, /analyze-data.sh. Analyze-data.sh is a file name. All of the other ones are directories or subdirectories. They start with a / as opposed to Windows, which is a \. Note everything is case sensitive, and spaces and names are discouraged. You can use dashes, underscores, other characters, but it's best not to use a dash. Don't use a space. The file system is how it appears. The top of the file system structure is /, which is root by the name. So the root of the whole file system is that directory represented by the /. The one on the next to the left is /bin. /bin is a short for binary, so that's often where executable commands are kept. The next one, /usr, often called user. That's where a lot of system files are. So in this case, we have a path to user local bin. So we have two directories with the same name, bin. And because they're in a different path, it's perfectly acceptable, but it can cause confusions having two directories with the same name. You note there the reference to absolute path. That is a path starting with the /. So starting from root, how do you get to bin? In one case, you just go /bin, but in the other case, you go /user /local /bin. If you're doing a relative path, you might start at local. If you're in the user directory /usr, the relative path to get to bin would be just local /bin, shown by here. So relative to where you're at now, or the absolute path starting at root. So then there's another example here of a file, home with the username, documents, HPC notes.txt. On our actual HPC, this is what it looks like as far as you can tell. So home is where you will log into by default, and this is where you tend to put your files. You have 50 gigabytes of space to put things into home. And what it actually looks like, and I'm using a hypothetical net ID of Kim. So the path for Kim could be home U13 Kim, and the U number is just something that the university provides to split up all of the users into manageable groups. You don't even have to worry about that. And then the next one is groups. each PI gets an allocation of 500 gigabytes, and you as a member of that PI's group can share if the permissions are set up right. So in this case, I've got a change directory to /groups/PI, and that'll take you to the directory with the PI's name. So replace PI here with the actual name of the PI. And just a quick note in front here, this is on a compute node, and this is the host name of a compute node on Puma. You don't have to learn these, but it helps to recognize that if it says R3U13N1 as the example rather than Genonia, which is a login node, you know you're on a compute node. This one is on one of the nodes on Elgato, and then the other example I have is a node on Ocelote. But all of these file systems are mounted on all of the clusters. So it doesn't matter which one you connect to, you can see the same structure. So the next directory I'm going to point out is temp, and this only exists on compute nodes as far as you can use. So we have /tmp, that's a file system directory on the specific compute node where you're logged into, in this case, CPU 38. And the last one I'll point out is xdisk. This is an optional on request path. And so if it has been requested, the PI again has the access to xdisk with the PI's name. So here's a logical view of how the structure looks physically. So we logged in as a user to the Bastion host, and we typed in shell, which took us to the login node. And then when we go to a compute node, they're all laid out there, and they all have access to the same shared storage. So this shared storage path is connected there. So doesn't matter which of the compute nodes are on, you can see the storage whether you're on a login node or a compute node, but you cannot see it from the Bastion host. You'll notice there's no connection from the Bastion to the shared storage. On the Bastion, there is nothing connected. On the login node, you can get to your home, your PI's group, or the xdisk if it exists. And on the compute nodes, the additional path you can get to is /temp, and that's temporary space to use during your compute jobs. On the bottom left is the file transfer node, and that's set up for quick data connections and for transferring large amounts of data. And it has attached to it as an extra connection to the rental storage. When you log in, you have an environment that's set up for you. So it has certain things by default. It has where you're logged into and certain, it has path statements to where you can run commands. So these things are set up for you, and I just have a reference to a few of them here, but I'm not going to go into any detail, just pointing out that there's an environment when you're logged in, and you can change the environment. Now we move on to file and directory commands. So here's just a few of them, and you can try these out. pwd, path to working directory, or print working directory. That's where I am right now. cd changes to another directory. Make dir creates a subdirectory from where you are now. Touch creates an empty file. rm removes the file, and then rm-r to remove a directory. cp to copy, mv to move. What move actually does is rename. So it keeps the files where they are on the disks, but changes the names of them. So it's actually really fast. It's not really moving data around as long as you're in the same file system. And then ls to list. Here are some commands you can try out to view files. So you'll get a chance to practice some of these. So if you want to see what your file looks like, but you don't want to look at the whole thing, you can use less, and it displays a screen at a time. Cat displays the whole thing, and it'll just scroll through the screen until it's done. Head prints the beginning, just the first few lines. grep is used for searching. So if you want to find all of the files that have the word house in them. Diff to compare two files. And tail is the opposite of head. Sort, you can sort in a file, find, look for files that meet your criteria. Word count is useful sometimes to count the words in a file. Okay, the first thing you're going to do, so sign into your account, should have that done, and then print the path to your current directory. That's one of the commands that was just shown on a previous screen. List the contents of the directory from your home directory, which is where you logged into, and you can double check to make sure you are in your home directory. And then we covered that command. Create a new directory, and then verify that it's there. Change to the new directory, and inside that directory, create a file, and then remove that file using the commands that were on the previous screens. Then for the next cases, we're going to pull in some files that have been created for this workshop. So you're going to use GitHub. Before you do that, create a Linux directory just to help you organize, and then change to the directory. And then from the directory that you just changed into, do a clone of the repository that University of Colorado set up for this. Once the git clone is done, then change directory, and suggest you try tab complete explore, that option. Then change to a directory under that, code Linux bash spinup, and then another one under that, scripts. And then from there, take a look at the scripts directory and see what's in it, and print the whole test.sh file. Look at the last few lines of another file, and then do a word count on another file. Right, so let's look at some of the files you are looking in there at, and get a little more detail of what the listings mean. So when you do ls-l, you'll get a long listing of the file. And the first thing that it shows is the permissions. So in the example here, the first file is actually a directory. And how do we know it's a directory? Well, it's coded in here as in blue. That's not really what tells that it's a directory. All the way at the beginning of the line is the D. So D represents a directory. And being in blue, system scripts is just helpful for you to indicate that. So what it says is it's broken up. So D for directory, and then we have 3 groups that are called octets. So the first group of 3, read, write, execute, is the RWX, and then more or less read, write, execute for the next one, although it's an S, not an X, and then read-X for the last one. So those are the different classes. The first group of 3 is for the owner and the permissions. So in this case, the owner can read a file, in this case a directory, write to it, or execute it if it has executables inside it. The next set of 3 is for the group, and the permissions for that, for the group, are read, write, and execute. Here's S, a sticky bit, so I suggest if you're curious, do a Google search on that. And then the third is other people. So what can they do? They can read it or execute it, anything in this directory. So the permissions here allow almost anything except other people who are not in the group cannot write into that directory. That means they can't modify existing files either. Then the next one down, called test, it's not a directory because it doesn't have a D. The owner can read or write. Everyone else in the group can read the files, and everyone else can read also. So those are the permissions. If you want to get in more detail to them and how they work, again, I suggest you Google or look in a more detailed training course. And this is just an overview of permissions. And how to change permissions. So you can play around with this. Chmod is generally called to change the mode. So there's an example here, chmod G plus WX. So to the group, add write and execute permissions on the file test. You can do it numerically as well. And that I'm not going to get into how the numbers are derived, but you can look those up if you're more curious. And then there's removing permissions. So that's O minus instead of plus. So you can play around in the directory in these scripts here to add permissions, remove permissions. Just experiment with it. So some of the different file types. I mentioned if it's got a D in front of it, it's a directory. But look at the third one. It's .anaconda. Anything that starts with a dot is hidden. And so in this case, it's blue. So that kind of indicates to you it's a directory, which is verified by the D at the front. So you have a hidden directory called Anaconda. And we'll get back to that. Then you got one in green, net test. So the green is indicative that it's executable. But how do you really know it's executable? And in this case, it's the X in the permissions towards the front. So the file is executable. You notice that the directory base is a directory, so it's not an executable file. So that's why it's not green. And then there's commands, ls, ls-l, which produces the long list shown here. And then you have to do the ls-la to see the hidden files like .anaconda. You can change directory to the directory above where you're at, or you can change directory all the way back to your home directory. I have a reference to symbolic links, also known as symlinks or soft links. They are commonly found on our HPC. And one of the main reasons for that is to not have to replicate data. So if you have a link to something, it looks like it's the file, but really it's empty. It's just to point it to the actual file location. So that can save space, not having to replicate. And it's also good for sharing files and also for naming conventions. So there's consistency. The actual file is in a place where it should be, but you're expecting it somewhere else. So what you see is actually a link to that file. So I've got an example here. You can do this yourself. So make a directory and then create a link or a file to an actual file. So the example here is to create one, and you're going to be in the scripts that you pulled down from git clone. You can try that. And then when you do ls-l, it'll show you what you've created. And the coding for it is in that pale blue. I want to point out file compression because it's inefficient to store many, many files in your directory structure. If you're not going to be using them for a while and you're just keeping them around, put them all in a tarball. You save space. And if you have to move the files to somewhere later on, like to an archive location, it's way easier and way faster just to move the tarball and not the actual thousands of files. So the command tar, which is short for tape archive, but it's a legacy name that goes way, way back. There's no tapes involved with this. So the command is tar, and the thing that you create is generally referenced as a tarball. So there's some commands here to create it, C to create, X to extract it, V for verbose can be a long listing. If you don't want to see what it's doing because it takes forever, you can skip the V. And then there's Z for additional compression. And the F is always needed because it says what the file name is going to be. So here's some examples. You can try creating some of these. When you're done creating them, do an ls-l and see how much space they take up compared to the original files that you had. All right, profiles. So I mentioned the files or directories that have a dot in front of them. One of the important ones is .bashrc. That is your profile when you log in. It's set by default, and it has a certain number of things that are set, but they get changed. And so the reason I bring them up is that you may not explicitly go in and change it. But if you're using Anaconda or Python, then when you set those up, say your Python virtual environment, it will make changes to your .bashrc. Now your environment has changed. And what happens sometimes is that the things that used to work in the way you expected don't work anymore because your environment has changed. So we get quite a few tickets for requesting help with something which used to work and now doesn't work and you don't know what changed. And then I just reference also the .bash_profile, which is another part of your environment setting, and then .bash_history, which is a listing of the commands that you've run. So actually that one's quite useful to look at the history to see what your commands you've run. And then there's also a history command which views this file. So quick reference to shells and shell scripts. So look at the image here on the bottom right. And I mentioned earlier the hardware is addressed by the kernel. So the kernel has all the drivers in it, how to deal with disks, memory, CPUs, all of the physical parts of the hardware that you don't really need to know about. And then the shell. So the shell are commands that talk to the kernel and wrap around, and then there's the applications on top of that. So for a shell, there are different ones, and this is open source. There are different ways of doing things. The one that we recommend and we really strongly prefer is Bash. There are other shells that people like to use. When you're running Slurm scripts, they should be, or I think actually need to be, in Bash. So that's the one that we really want you to use. And so I have an example here of just the simplest of shell scripts in the blue. So the first line indicates that it's a Bash shell script. The next line starts with a hash symbol, and that represents a comment, except for the first line. And so it's just instructions. So those are really good to put in a script to remind you of what you've done. And then the next thing is a command. So change directory to temp, and then run another command, ls. So that's a really simple script. And so we have an example here for the next little exercise. So you want to be in that same scripts directory that you went to before from the git clone, and use commands less and cat, run one of the scripts. So you notice they end with .txt, but that's just a convention of practice. There's nothing that says that a text file or a script has to end with .txt. And then same with hello.sh. So that just indicates it's a shell script, but it doesn't have to have that at the end of it. It just makes it easy to understand what it is. And then we have you change permission to make it executable. So you run it, and if it doesn't work, change permission, and then try to run it again. And then just a quick reference back to the on-demand. So you can do this with on-demand. So there's an example of managing your files. But let's go look at it on using the editor. There is Nano, VI, or Vim, it's known, and Emacs. And then there's another one I have referenced here. So Nano is pretty simple, and it's a good one to get started practicing if you want to just do some editing. And then I've got an example here. So you can do nano space and then one of the files, hello.sh, for example, and then note the options at the bottom to get out of there, Command X to exit. You can search for things, check spelling. There's some just really basic. So we have an exercise, go into Hello World and edit it, and then run it. So you can change the text comments in there to display something different. And then we have just a reference here at the end to some more resources. So if you want to get to these, go to our documentation and go into the training, and you'll find the PDF for this, and then you can follow those links. So thank you for watching, and I hope you found this valuable.